New York City's water tunnel. Number 1 has been running without stopping since 1917. The city cannot shut it down to inspect it. They don't know its full condition. And it was built by men using hand tools, mules, and gunpowder. What follows is a record of specific engineering methods that let builders in the 1800s put water systems in the ground that are still carrying water today. Systems that modern cities have tried to replace and could not. One of those systems was built with a redundancy feature that modern engineers didn't realize was intentional until they tried to repair it, 140 years later. We'll get there. Number 1. The Croton Aqueduct Gravity Feed System. The Croton Aqueduct, finished in 1842, ran 41 miles from the Croton River to distributing reservoirs in Manhattan, entirely by gravity, no pumps, no power source of any kind. The fall from source to city was 13 inches per mile, held consistently across 41 miles of hills and valleys. They surveyed every inch using rods, levels, and printed slope tables. No electronics, no laser transit. The water ran exactly as calculated on the first day it was let into the channel. Portions of that gravity feed are still active today. Number 2. Hydraulic lime cement. Modern Portland cement starts breaking down in wet environments within decades. The cement lining the Croton Aqueduct has been in contact with flowing water since 1842. Most of it is still sound. The formula was hydraulic lime, a mix that cures harder in the presence of water, not weaker. Portland cement is cheaper and faster to set. It is not tougher over a long span of time in a wet environment. They knew the difference. The decision to stop using the better material was not an engineering decision. Number 3. Cut and cover tunneling. In 1842, workers dug distribution tunnels under Manhattan streets that were still being used. No detour systems, no hydraulic excavators. The method was cut and cover. Open the street in sections, dig the trench, line it, arch it over, close it back up, move forward. The arched brick covers were self-supporting from the day the keystone went in. No section collapsed under live street load. The work went forward through a full New York winter. Number 4. Hand-surveyed grade tolerances. 13 inches of drop per mile, held for 41 miles. To hold that grade, the survey crew moved a leveling instrument thousands of times across the full route. A telescope on a calibrated base read against a rod held by a second man at distance. Each setup gave them a sight line accurate to fractions of an inch. Modern surveyors use GPS and digital levels. Their equipment is faster. It is not, by the records, significantly more accurate on a project of this type. Number 5. Boston's Cochituate Aqueduct Brick Barrel Vault. The Cochituate Aqueduct, finished in 1848, carried water into Boston using a continuous brick barrel vault, a self-supporting arched channel running for miles underground. The arch geometry was calculated by the masons laying it, not by an engineer standing over them with drawings. Those men understood load transfer through an arch the way a mechanic understands torque, not from a textbook, from years with the material. Some sections of that vault are still intact. Number 6. Reservoir siting logic. Every major American city that built its reservoir system before 1880 sited those reservoirs at high points above the city. The elevation difference between the reservoir surface and the delivery point created pressure, natural, passive, permanent, with no pump required. When those reservoirs are eventually decommissioned, the pressure those districts have received for free will need to be replaced with electricity and pumps. That cost will recur forever. The original cost was paid once. Number 7. Workforce organization. By the accounts of workers who built it, the Croton Aqueduct project maintained consistent construction tolerances across a workforce with no unified training, no standardized tools, and no safety regulation. The system that kept the work accurate was direct oversight by master masons who checked every section by eye and by hand, using a curved wooden form pressed against the finished arch to confirm geometry before the next course of brick was laid. Civil engineers, 180 years later, still point to this work as a reference, not as a curiosity, as a reference. Number 8. Gatehouse valve mechanics. The cast iron gate valves on the Croton and Cochituate systems were hand-operated, gear-driven, and built to be serviced by one man with hand tools. The gate seated against a machined bronze face. The stem packing could be tightened without dropping line pressure. The gear ratio let one man fully open or close a valve on a main carrying thousands of gallons per minute. These valves have been sitting in damp stone buildings for 150 years. The ones that haven't been replaced still work. They built these with no electricity. None. Number 9. The deliberate redundancy system. When repair crews entered a section of the new Croton Aqueduct in the 1990s, they found something not in the drawings. A secondary chamber built into the main conduit wall, sized to carry bypass flow if the primary channel failed. They logged it as an anomaly. It took time to confirm it was not an error. It was designed in. The men who built this in the 1890s had calculated for a failure condition that hydraulic engineering wouldn't formally name for another generation. They didn't know the theory. They knew the water. Number 10. Pressure surge engineering. Water hammer, the pressure spike when fast-moving water is suddenly stopped, was understood by engineers in the 1870s well enough that they built against it. Expansion chambers were designed into distribution mains at calculated intervals, giving pressure spikes a place to go before they could damage pipe joints or valve seats. The same principle was patented as new technology in the 1950s. The 1870s version was cast iron and masonry, no moving parts, no maintenance. It worked on physics alone. Nobody teaches this in civil engineering programs anymore. I checked. Number 11. Infiltration gallery water collection. An infiltration gallery is a horizontal well, a perforated pipe buried in the gravel bed of a riverbank. Water seeps through the natural gravel, which filters out suspended solids and biological material and enters the gallery already clean. American engineers in the 1870s and 1880s built these as primary collection systems. They worked. They kept working. And then, within a 20-year window at the turn of the century, nearly every American city that had one stopped using it. The question of why and who benefited we'll come back to. Number 12. Why gravity systems were replaced. Gravity-fed systems have one feature that made them a problem for certain businesses. They run without ongoing cost. Once built, the water moves. No fuel, no contracts, no parts. Utility records from the period suggest pressure on municipal water boards came not just from engineering arguments, but from franchise interests. Companies that stood to gain service contracts once pumps were in the ground. Pumps need fuel. Fuel needs a supplier. Suppliers need contracts. The gravity system needed none of that. Number 13. Rosendale Cement. Rosendale Natural Cement came from Ulster County, New York. It set slowly, too slowly for contractors pricing jobs by the day, but what it produced was a superior material Portland cement cannot match in wet or submerged conditions. The Brooklyn Bridge anchorages are Rosendale cement, and so is the base of the Washington Monument. Production ended in 1970 because Portland cement was cheaper. When the Statue of Liberty underwent major restoration in the 1980s, engineers found nothing currently made could match the original foundation work. They restarted a Rosendale mill specifically for the job. They revived a formula killed by the market to fix a structure the market's preferred product couldn't touch. Number 14. What NYC spent trying to replace Tunnel Number 1. New York began Water Tunnel Number 3 in 1970, needed in part because Tunnel Number 1, running since 1917, never inspected, could not go offline without cutting water to large parts of the city. The cost passed $6 billion. Tunnel Number 1 still carries water today. The 1917 tunnel, drilled by hand and hauled out by mule, remains in service while its replacement has been under construction for 55 years. The system they cannot replace is the one they cannot afford to admit still works. Number 15. The Infiltration Gallery. Answer. Infiltration galleries required no chemicals. No chemicals means no supplier. No treatment plant means no contractor, no certification requirement, no oversight structure. The water came out of the ground clean because the ground cleaned it. You can't sell a contract on geology. Between 1890 and 1910, American cities switched to surface intakes feeding centralized treatment plants. Those plants required chlorine. Chlorine required a supplier. That system is what every American city runs today. It requires continuous spending to function. The moment the spending stops, the water stops being safe. The infiltration gallery required nothing after it was built. That is why it went away. Right now, 40 feet below a street in Lower Manhattan, water is moving through a brick-lined tunnel that has not been inspected since the men who built it were alive. It is holding pressure. It is flowing at design volume. Built by men with hand tools, for a cost that would not cover a single mile of the tunnel, started 55 years ago to replace it. The men who built that tunnel didn't sell the city a dependency. They built something and left. The city has been paying ever since for the privilege of forgetting how that was done.